welcome to the class. Today we are going to focus upon the ideal Brayton cycle. Till time we have seen that there is gas turbine, then there are different attachments to the gas turbine, and it is possible that this gas turbine can be considered as a possible engine for the aircraft propulsion. So now let us understand the gas turbine cycle from the thermodynamics viewpoint. So air standard Brayton cycle. Here we are assuming that air is the working medium and it is not changing its properties in the process of the engine or in the thermodynamic cyclic process. And further we are also considering that the thermodynamic properties of air, which are specific heat and specific heat ratio, they are not going to change with respect to temperature. So we are considering air as a calorically perfect gas. So in view of this, let us plot the thermodynamic cycle. We had already considered this thermodynamic cycle while considering different cycles in the overview of thermodynamics. So in this process we will replot the thermodynamic cycle, which is a Brayton cycle. So let us first plot TS diagram. On y-axis we have temperature and on x-axis we have entropy. So first process is 1 to 2, it is an isentropic process. Then process 2 to 3 is an isobaric process. Then process 3 to 4 is an isentropic process, and process 4 to 1 is an isobaric process. So this is entropy constant process. 3-4 is also entropy constant process. 2 to 3 is pressure constant process, and 4 to 1 is also pressure constant process. This is the air standard Brayton cycle. Let us plot the PV diagram for the Brayton cycle. As per the PV diagram, process 1 to 2 is isentropic compression, process 2 to 3 is isobaric heat addition, process 3 to 4 is isentropic expansion, and process 4 to 1 is isentropic heat rejection. This is PV diagram for Brayton cycle. Now let us plot HS diagram for Brayton cycle. So HS diagram is similar to the TS diagram, except slope is different. So geometrically it will look like similar. So 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant pressure heat rejection. So now what are the processes? Process 1 to 2, as what we said, it is isentropic compression process, and we had also said in one of our earlier classes that it is unlike in SI engine. In SI engine there are different processes, but all the processes are conducted in one unit. However, in gas turbine each process will be conducted in different unit. So isentropic compression will be conducted in compressor, and then process 2 to 3 is isobaric heat addition. So we add heat here. So there is Q in, there is W in, and this process is conducted in combustor or combustion chamber. Process 3 to 4 is isentropic expansion. So this is a process in which work is done, and then this is done in turbine unit. So this is W out, and then process 4 to 1 is isobaric heat rejection, and this process is conducted either in atmospheric condition or in case of open cycle or in a pre-cooler. So we will see this in detail. So this is air standard cycle, which is a Brayton cycle. Now let us plot the schematic or the diagram which is possible engine for the Brayton cycle. We had already considered it multiple times. So first is open cycle. So in case of open cycle, first process, as what we said, process 1 to 2 is compression. So this is 1 to 2 and it is getting done in compressor, and then we have combustion chamber, and from the combustion chamber the gas goes to the turbine, and then this gas goes back into the atmosphere, and this is taken from the atmosphere. Here we practically feel that this is an open cycle, since the same gas which is coming at the exhaust of the turbine is not going into the compressor. So we are having this as an open circuit. So this is an open cycle for gas turbine power plant. However, we consider the same amount of mass flow rate of the gas is coming into the compressor at initial temperature 1. So we say that this is a open, and then this is a cycle. Then there is closed cycle gas turbine power plant, and in case of closed cycle gas turbine power plant, again there will be compressor first, and from the compressor gas will go, air will go into a heat exchanger. So this is a heat exchanger, this is a heat exchanger, and then from the heat exchanger it will go to the turbine, and then from the turbine it will go again to a heat exchanger, which is called as precooler. But these two heat exchangers will have another fluids which will pass the heat or which will take the heat. So in case of heat exchanger, which is plotted over here, we are interested in getting heat into our system, and then that's why a hot gas will be passed in the heat exchanger, such that that gas will give heat to the air at constant pressure, process 2 to 3. After 3 to 4 expansion, a precooler will have a cold gas which will be, or cold fluid which will be taking heat from the air which is undergoing the process 4 to 1, which is a constant pressure heat rejection process. This is a precooler. These are the diagrams for the schematic diagram for the Brayton cycle. So having said this, we will move ahead and see what are the relations for the thermodynamic processes and associated work and heat interactions. So for that, let us first plot the TS diagram. In case of Brayton cycle, you would see that we repeatedly plot the TS diagram, since it helps us to analyze, understand the basics of the Brayton cycle. So in each case we will plot the TS diagram. So heat and work interactions, as what we said, let us first consider the process 1 to 2. So process 1 to 2. In the process 1 to 2, it is isentropic compression. As the name suggests, in this process Q12 is equal to 0, and then we need to find out work interaction in the process 1 to 2. We had seen that for the steady flow energy equation, if we apply for the process 1 to 2, we can say that m dot is equal to h1 plus v1 square by 2 plus gz1 plus q12 is equal to m dot into h2 plus v2 square by 2 plus gz2 is equal to w12. We will neglect change in potential and kinetic energy change in the compressor. We also know that heat interaction is 0, so we have m dot into h1 minus m dot into h2 is equal to w12. Rather, if we are interested in working out the specific work, then this is having unit kilojoule, but let us consider the work kilojoule per kg per second, so this is having unit kilowatt. So W12 is equal to H1 minus H2, and this is having unit kilojoule per kg, or it is having unit kilojoule per kg. So that is the unit what we are giving for the specific work obtained from the difference of enthalpy is H1 minus H2, but this is work done in the process of compression. But we know that process of compression is work input process, so practically modulus of W12 is H2 minus H1 with the unit kilojoule per kg. So as far as work and heat interactions are considered, Q12 is 0 and W12 is H2 minus H1. Now consider process 2 to 3, process 2 to 3 for work and heat interaction. So W12 is H2 minus H1. Since it is compressor, so we will say WC is equal to H2 minus H1. Now process 2 to 3. Process 2 to 3 is isobaric heat addition, but in case of process 2 to 3 we have W23 is equal to 0, and then we will also neglect the change in potential and kinetic energy in process 2 to 3. So again consider specific quantities, so it would become H1 plus Q H2 plus Q23 is equal to H3. So this leads to the fact that H3 minus H2 is equal to Q23, or Qin is equal to Q23 is equal to H3 minus H2. So we have heat input in the process, isobaric process 2 to 3 is H3 minus H2. Further, we are considering it as an ideal gas, so we can say it with one more formula where enthalpy is Cp into T. So Cp into T3 minus Cp into T2. We are considering specific heats as constants. So Qin is equal to Q23 is equal to Cp into T3 minus T2. Similarly, for compressor work, we can replace enthalpy with temperature as Cp into T2 minus Cp into T1. So we get compressor work as Cp into T2 minus T1. Then let us work for process 3 to 4. It is isentropic expansion, and in the process 3 to 4 we again have Q34 is equal to 0. The derivation for work and heat interaction is same as what we did for process 1 to 2. So process 3 to 4 has Q is equal to 0, and then we have H1 is equal to H3 is equal to H4 plus W34. So W34 is equal to H3 minus H4, but W34 is turbine, so it is WT. So WT is W34 and it is equal to CPT3 minus CPT4. So WT is equal to W34 is equal to Cp into T3 minus T4. So this is turbine work which can be obtained from the temperature difference across the turbine and also its multiplication with specific heat. So let us consider process 4-1, and that is isobaric heat rejection. In this process is getting conducted in pre-cooler. So for that we have W41 is equal to 0, since it is only heat interaction process. Further, we will also neglect potential and kinetic energy changes. Consider specific quantities, so it leads to H4 plus Qin is equal to H5. So Qin is equal to H5 minus H4, but we know this process is heat rejection, so Q out is equal to is equal to H1. So Q in is equal to H1 minus H4 and Q out is equal to H4 minus H1. So Q out, once it is represented in terms of specific heat, it is CPT4 minus CPT1. So Q out is equal to Cp into T4 minus T1. So this is how we can find out work and heat interactions in the process, in any process for the gas turbine power plant. Thus, let us move on to find out state variables for our ideal Brayton cycle. Again, for that, let us plot a TS diagram for Brayton cycle, and we are considering, as what we earlier have said, simple air standard cycle with 4 processes for Brayton cycle, and they include 2 isentropic processes and 2 isobaric processes. So in case of Brayton cycle, whenever we are dealing with examples or in general, for design perspective, the known quantities for us are in general pressure ratio, which is P2 by P1, but P2 is equal to P3 and P1 is equal to P4. We would also know the initial quantities, which is temperature at the inlet to the compressor, which is also called as minimum temperature of the cycle. We would also know P1, which is the condition at the entry to the compressor. Further, we know that which gas we are using, so gamma and specific heat, they are the thermodynamic quantities of a gas, so they would also be known to us. And further, we would be knowing that maximum temperature of the cycle, which is Tmax, or what we would be knowing either is Qin. Here the temperature maximum of the cycle would be constraint from the material perspective, that we cannot cross certain temperature due to the material point. So maximum temperature has a fixed limit depending upon the materials, that will also be known to us, or we would be knowing the heat input which is given in the process of the heat addition. So these things will be known to us. Knowing these things, we are expected to find out rest all the quantities from the gas turbine power cycle, which is Brayton cycle. So state 1. In the state 1, we know P1 and T1. So we don't have to calculate anything in the state 1 since they are known to us. Now let's move to the state 2. And in the state 2, we just know Rp is equal to P2 by P1, which is said as pressure ratio. For Brayton cycle, pressure ratio is a governing parameter, and Brayton cycle is defined with a pressure ratio, and this is the limit of the pressure between P2 ratio between P2 and P1, where P2 is the maximum pressure of the cycle and P1 is the minimum pressure of the cycle. So this pressure ratio is governing parameter, and that will be known to us, or we have to define it priorly in the design process. So from this we know P2 is equal to Rp into P1. Then we can find out temperature at the state 2 using the formula for isentropic process, which is T2 by T1 is equal to P2 by P1 bracket raised to gamma minus upon gamma, and then this is basically Rp raised to gamma minus 1 upon gamma, and it leads to T2 is equal to T1 into Rp bracket raised to gamma minus 1 upon gamma. We are going to state Rp raised to gamma minus 1 upon gamma as C. So we have T2 is equal to T1 into C, since this is a constant. Then let us move to state 3. In the state 3, for us, let us assume that we know Q in. So let us assume that Q in is known. For state 3, P3 is equal to P2 is equal to Rp into P1. So P3 can be evaluated. Since we know Q in, we know that Q in is equal to Cp into T3 minus T2. We have said, we have derived this from the work and heat interactions for different processes. Knowing this, we can find out T3, where T3 is equal to T2 plus Q in divided by Cp. So this is how we can find out pressure and temperature at state 3. But if T3 is known to us a priorly, then we don't have to evaluate this, since we already know P3 and we can also know T3 from the design constraints. So this is how we can evaluate everything at state 3. So let us find out the properties at state 4. So for state 4, we know that P1 is equal to P4, so P4 is known to us. Further, we want to know T4, then T4 upon T3 is equal to P4 upon P3 bracket raised to gamma minus 1 upon gamma, which is 1 upon Rp bracket raised to gamma minus 1 upon gamma, since Rp is equal to P2 by P1, which is equal to P3 by P4. So we know that T4 by T3 is equal to C is equal to 1 upon C. So we have T4 is equal to T3 by C, or T3 by Rp raised to gamma minus 1 upon gamma. So knowing all the things this way and knowing all the corners of the Brayton cycle, we can proceed to find out the performance parameters of the Brayton cycle. Among those performance parameters, one is the net work. So net work of the Brayton cycle is turbine work minus compressor work, since here is the turbine process where we do work. However, in the case of compressor, we take work. So Wt minus Wc is net work. So net work is equal to H3 minus H4 minus H2 minus H1. So W net is equal to Cp into T3 minus T4 minus Cp into T2 minus T1. This is how, knowing the all parameters or all the state variables, we can find out W net. Further, we can also find out efficiency from the fact that it is W net upon Q in, where W net is known to us, which is Cp into T3 minus T4 minus Cp into T2 minus T1 and whole divided by Q in, and we know heat interaction or heat addition process is process 2 to 3, so it is Cp into T3 minus T2. So this is how, once we know some design variables, we can estimate other variables at different states, and then using those variables we can find out the net work in the Brayton cycle and the efficiency of Brayton cycle. Having said this, we can move ahead and find out what is the optimum work done in case of the Brayton cycle. So again, let us plot the Brayton cycle, which is known to us from the TS diagram as process 1 to 2, 2 to 3 and 3 to 4. So here we said that W net is equal to Wt minus Wc, where W net has turned out to be Cp into T3 minus T4 minus Cp into T2 minus T1. So let us take Cp common from all, so it will be T3 minus T4 minus T2 minus T1. Let us further take T1 common, so it will become Cp T1 into T3 by T1 minus T4 by T1 minus T2 by T1, sorry, here it is plus, so plus 1. Now from this we know that T3 by T1, here T3 by T1 is equal to T max upon T min, and this is a fixed quantity which is a design parameter, and that is beta, and it is known to us. So it's a constant and it's a known quantity. So from this we can write W net is equal to Cp T1 into beta minus T4 by T3 into T3 by T1 minus T2 by T1 plus 1. We replaced the term T4 by T1 as T4 by T3 into T3 by T1. Using this we can get W net is equal to Cp T1 into beta minus T4 by T3. From the isentropic relation, it is Rp raised 1 upon Rp raised to gamma minus 1 upon gamma, and T3 by T1 is beta. So minus T2 by T1, we know it is from isentropic relation Rp raised to gamma minus 1 upon gamma. So knowing these basic quantities, we can find out W net from the design parameters. However, as it is evident that specific heat, temperature, they are known quantities. Temperature is known at the inlet, Cp is fixed for the working field, beta is a known and constant quantity, gamma is also known and constant quantities. So here it is evident that W net is dependent upon only pressure ratio. So it has dependence of pressure ratio. So for optimization, let us differentiate the expression with respect to d by drp of W net and equate it to 0 such that we will get the maximum network condition or value of Rp for which W net will be maximum. So from this we get d by drp of W net is equal to, let us differentiate this expression, then we will get this first term will be 0 since everything is constant, and then for the second term we will get Cpt1 into minus gamma minus 1 upon gamma into Rp raised to minus gamma minus 1 upon gamma minus 1 minus Cpt1 into gamma minus 1 upon gamma into Rp raised to gamma minus 1 upon gamma minus 1, and differentiation of 1 will be 0 and everything is equated to 0. So in this case Cpt1 gets cancelled, and then we can get Rp optimum bracket raised to gamma minus 1 upon gamma equal to square root of T3 by T1, square root of T3 by T1. Basically this is known to us, so which is beta. So this is the condition for Rp optimum. If we know T3, if we know T1, then we can take square root of that ratio, and then that would be our optimum Rp, and that would lead to maximum network. Further, we know that T3 upon T1, in an imaginary case, let us consider that we compress the gas till T3. We compress the air till the temperature T3. Then in that case, after the process of compression, we will get the temperature which is T2 and the ratio is T2 by T1, but in this ideal case T2 is equal to T3, and then this is Rp max bracket raised to gamma minus 1 upon gamma. So Rp optimum practically is square root of Rp max. This is the definition for Rp optimum. So knowing this, we can find out what are the basic things about Rp optimum. Now we have got that Rp optimum bracket raised to gamma minus 1 upon gamma is equal to square root of beta is equal to square root of T3 by T1. Okay, but we know that Rp optimum bracket raised to gamma minus 1 upon gamma practically is equal to T2 by T1, or it is equal to T3 by T4. So T2 by T1 is equal to square root of T3 by T1. This leads to the point that T2 is equal to square root of T3 into T1. So T2 is equal to square root of T max into T min. Similarly, T3 by T4 is equal to square root of T3 by T1. So T4 is equal to square root of T3 into T1. So T4 is also equal to T max into T min. So practically we mean that for Rp optimum condition we have T2 is equal to T4. So practically we mean that the TS diagram will have 2 points which are at same height. So this is compression, heat addition, expansion, and then T2 is equal to T4, and then we have heat rejection. If we have the pressure ratio lower than Rp optimum, then in that case we will go like this after compression, and let us assume that T max is same, so we have to go till here and then we will come back and we will have some R dash, and then this is still 3 dash which will have same temperature. Now this case will have lower network output since exhaust temperature is more, so more heat is rejected, so that is why we will have lower work output. So further, in this case, if we have more compression ratio than optimum for the same T3, then we will go like this and then we will expand in this way, and so this becomes 3 double dash and this will be 4 double dash. Here we can see that more compressor work is there in comparison with the turbine work. So turbine work is here, compressor work is here. So since compressor work is more than turbine work, we will have lower heat network than the optimum case. So only one case has maximum network output. Having said this, let us move on for the definition of efficiency, and we know efficiency is equal to W net upon Q in, which is equal to Wt minus Wc upon Q in. So efficiency is equal to, from the Brayton cycle, turbine work is Cp into T3 minus T4, compressor work is Cp into T2 minus T1, and Q in is Cp into T3 minus T2. So Cp can be cancelled, so T3 minus T4 minus T2 minus T1 divided by T3 minus T2. Further we can rearrange the term and we will have Cp T3 minus T2 minus T4 minus T1 divided by T3 minus T2. This step is nothing but we are saying that efficiency is equal to Q in minus Q out divided by Q in. since Cp into T3 minus T2 is Q in and Cp into T4 minus T1 is Q out. So efficiency is 1 minus T4 by T1 divided by T3 by T2. We know that. Let us write down this as T4 is equal to T3 divided by Rp raised to gamma minus 1 upon gamma. We know that it can be evaluated from the known state variables. Minus T1 divided by T3 is again the same thing, and T2 is T1 into Rp raised to gamma minus 1 upon gamma. So efficiency becomes 1 minus 1 upon Rp raised to gamma minus 1 upon gamma into T3 minus T1 into Rp raised to gamma minus 1 upon gamma divided by T3 minus T1 into Rp raised to gamma minus 1 upon gamma, and it gets cancelled. So this leads to efficiency is equal to 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So efficiency depends only upon pressure ratio for given gamma. So for a given gas, Brayton cycle efficiency depends only upon the pressure ratio, or for a given pressure ratio it depends only upon the gamma or specific heat ratio of the gas. Now let us find out a new term which is called as work ratio or back work ratio. So here we will define Rw as work ratio, and it is defined as the ratio of net work to the turbine work, and we have said that this work ratio has to be close to 1, and if this ratio is close to 1, then this ratio indicates that the cycle's efficiency is not dependent upon or less sensitive to the component efficiency. So this has to be evaluated as a performance parameter. But W net is equal to Wt minus Wc divided by Wt. So Rw is equal to 1 minus Wc upon Wt. We know from work and heat interaction that Wc is Cp into T2 minus T1 and Wt is Cp into T3 minus T4. Further, Rw is equal to 1 minus Cp gets cancelled, T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma minus T1, and T3 is as it is, and T4 is T3 divided by Rp raised to gamma minus 1 upon gamma. So Rw is equal to 1 minus, from the numerator we can take T1 common, from the denominator we can take T3 common, and then we have Rp raised to gamma minus 1 upon gamma minus 1 divided by 1 minus 1 upon Rp bracket raised to gamma minus 1 upon gamma, and this leads to Rw is equal to 1 minus T1 upon T3 into Rp raised to gamma minus 1 upon gamma, which is nothing but Rw is equal to 1 minus Rp raised to gamma minus 1 upon gamma divided by beta. So this is the formula for work ratio for a Brayton cycle. From the known Rp, known beta, and known gamma, we can find out what is the work ratio. There is one more term which is RB, which is back work ratio, and back work ratio is defined as compressor work divided by turbine work. So similarly, we can derive an expression for back work ratio as well. Knowing the temperatures and corresponding relations, we can find out what is the back work ratio. So these are the derivations for work ratio and back work ratio. There are certain observations for the Brayton cycle, and as per those observations we can try to analyze what do we get an extra insight for the Brayton cycle. So here, while plotting the Brayton cycle, we have to take an extreme care such that the process 1 to 2 to 3 and process 4 to 1, they are isobaric processes. So let us write down the combined first and second law formula, which is TdS is equal to dH minus VdP, but for constant pressure process we have TdS is equal to dH, so this term vanishes. So TdS is equal to Cp dt, and this leads to dt by ds at constant pressure is equal to T by Cp. So this is the slope of constant pressure line on the TS diagram. So the slope of process 2 to 3 is increasing as the temperature increases. So this is a curved line which has increasing slope from 2 to 3. Similarly, process 4 to 1 has decreasing slope from 4 to 1. Hence, the constant pressure lines diverge on the TS diagram. This is first observation. Second observation, we have seen that efficiency is equal to 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. Then from that it is evident that if pressure ratio increases, this leads to efficiency increase, and if gamma increases, then also efficiency increases. From the formula for the work ratio, which was Rw is equal to 1 minus Rp raised to gamma minus 1 upon gamma divided by beta, we know that as the pressure ratio increases, work ratio decreases, and as beta increases, work ratio increases. So these are certain observations for the Brayton cycle. Now next point to be noted here as W net, then we can know that W net is equal to Wt minus Wc, and we have said that W net as Cpt1 into bracket T3 by T1 minus T4 by T1 minus T2 by T1 plus 1. So we get W net upon Cpt1 is equal to beta minus beta upon Rp raised to gamma minus 1 upon gamma minus Rp raised to gamma minus 1 upon gamma plus 1. We have said C is equal to Rp raised to gamma minus 1 upon gamma. So W net upon Cpt1 is equal to beta minus beta by C minus C plus 1. Here we can take this formula and we can plot the variation of W net for different betas. So this would be W net upon CPT1 on y-axis and RP on x-axis, we would get something like this. This is for particular value beta 1, this is for particular value beta 2, and then this value is beta 4, where betas are increasing in this direction. Similarly, if we would have plotted efficiency versus RP, then we would have got a plot like this, and then this, and then this. This is for gamma 1.28, this is for gamma 1.4, and this is for gamma 1.6. So in this direction gamma increases. As we have said, efficiency increases with RP and efficiency also increases with gamma. In case of WNet, we have seen that for a particular RP, WNet is maximum. Then this gamma 1.28 represents triatomic molecule, gamma 1.4 represents diatomic molecule, and gamma 1.66 represents monoatomic molecule. And then thus we have seen that how to deal with ideal Brayton cycle or air standard Brayton cycle, and how to evaluate different state variables, performance parameters, and what are the observations from their derivations. We will see next things in the next classes. Thank you.